So diffraction grating experiment questions. So a diffraction grating is 400 lines per millimeter. Underline that. It is placed 80 centimeters from a screen and monochromatic light passes through it. The distance between the two second order images on the screen is 54 centimeters. Calculate the wavelength of the light. Now it's a little bit unusual because it's hard to write down your list, but you know this is the formula and you're looking for the wavelength of the light. Okay. You are told a second order image, so we know n is equal to 2. That's grand, so we have that. Okay, we want a wavelength, so we need to have d. It has 400 lines per millimeter, so we know that d is 1 over number of lines per meter. Okay, so that's the way we do it, so 1 over 400,000, because there's 400 lines in a millimeter, 400,000 in a meter, multiplied by 1,000. They do it slightly differently in one of the clips that you've just seen. 1 divided by, but it's the same idea. Okay, so we end up with 2.5 by 10 to the minus 6 meters. By 10 to the minus 6 meters. So that's our d, we're sorted on d. So remember, if you don't have d, that's what you always use. If we don't have theta, and we're given distances, we sketch. Okay, you always sketch in this situation. So we have n equal to 0. We're interested in n equal to 2. There's clearly 2 of those, one on either side. You're told the distance between those is 54 centimeters. Let's change it to, okay, we could leave it in centimeters because we're going to be doing a ratio, but we're going to, it's as easy to change it to meters. So 0.54 of a meter. Okay, and you're told the distance from the grating to the screen is 80 centimeters or 0.8 of a meter. Remember, you're interested in this angle. So it's not 54 centimeters we want, it's 27 or 0.27 of a meter. So when we that sketched out, you can see clearly, remember, socket to a right angle triangle we use all of the time. So in this case, it's the tan of the angle opposite over adjacent. Tan of the angle 0.27 over 0.8. You can see as a ratio, you could have left that as centimeters, but I didn't. So we want to get second function 10, so the inverse of 0.27 over 0.8. Okay, we're getting 18.65 degrees. Okay, so basically, remember, if you're not given d, we use this, and we're getting the d is the grating constant. If we're not given the angle, very often we do this. We also have to be careful regarding, are we talking about the 0 to the second order image or the second to the second order image when we're given values? So always watch that. We're no business because we have n, we have d, and we have theta, so we've only one unknown. So now it's where the hard work is done. So 2 times the wavelength, d is 2.5 by 10 to the minus 6, sine of 18.65. So 2 lambda is 2.5 exponential minus 6 multiplied by sine of 18.65. Okay, so we're getting 7.99, so 7.99 by 10 to the minus 7. And then there's going to be half of that. Okay, so we're getting 3.997, or basically 4.00. by 10 to the minus 7 meters, which makes sense. Okay, we can change that to nanometers, remember, by multiplying by 10 to the power of 2. Okay, if you want 4.00 multiplied by 10 to the minus 7, change it to nanometers, divide by 10 to the minus 9, and you get 400 nanometers. Okay, you only have to do that if you're told to do it. Okay, you don't have to do it otherwise. Remember, visible light, and it's worth remembering this, 300 to 700 nanometers. So if you're in that area of 3 by 10 to the minus 7 to 7 by 10 to the minus 7, you know you're in business. Okay, if you can do that one, you can do any of those. Full stop.